Yes, there are deductions to consider to reduce the calculated load. Since the building has separate systems for heating, ventilation, and air conditioning, or HVAC, and emergency lighting, the calculated load can be reduced by these values. Assume a heating, ventilation, and air conditioning load of 0.5 watts per square foot for the occupied area, which would be 10,000 square feet times 0.5 watts per square foot equals 5 kilowatts. Assume an emergency lighting load of 0.1 watts per square foot for the entire area, which would be 22,000 square feet times 0.1 watts per square foot, which equals 2.2 kilowatts. Total heating, ventilation, and air conditioning and emergency lighting load deduction 5 kilowatts plus 2.2 kilowatts equals 7.2 kilowatts or 7.2 kilovolt amps. The calculated load assumes 100% demand for occupied areas. However, in reality, the actual demand is typically lower. A reasonable assumption for office space is to consider 50% demand for occupied areas. For the 10,000 square foot occupied area, the calculated load would be reduced by 48,140 volt amps times 50% equals 24,070 volt amps. The common hallway and elevator space is typically not fully utilized, so a lower demand factor can be applied. Assume a demand factor of 25% for a 7,000 square foot common area. Calculated load reduction 7,000 square feet times 4.5 watts per square foot times 25% equals 787.5 volt amps. Original calculated load 123 kilovolt amps. Heating, ventilation, and air conditioning and emergency lighting load deduction negative 7.2 kilovolt amps. Occupancy deduction negative 24.7 kilovolt amps. Common area load deduction negative 787.5 volt amps. Revised calculated load 123 kilovolt amps minus 7.2 kilovolt amps minus 24.7 kilovolt amps minus 787.5 volt amps equals 81.12 kilovolt amps. Actual load 115 amps alternating current per phase times 3 phases times 120 volts equals 41.4 kilowatts or 41.4 kilovolt amps. Revised calculated load 81.12 kilovolt amps. The revised calculated load is still higher than the actual load, but it is significantly lower than the original calculated load. This suggests that there may be additional factors contributing to the lower actual load, such as energy-efficient lighting fixtures, occupancy sensors that turn off lights when areas are unoccupied, and variable speed drives on heating, ventilation, and air conditioning systems. Based on the deductions and revised calculation, it can be argued that the actual load is within the capacity of the existing 800 amp service and that the proposed 350 amp meter fitting is feasible. However, it is essential to present a clear explanation and supporting documentation to demonstrate the accuracy of the calculations and the validity of the proposal. When calculating electrical loads in a high-rise building, several factors should be considered to ensure an accurate assessment of the building's electrical demand. This is especially important when planning for new installations, renovations, or when subdividing existing tenant spaces. A precise calculation helps prevent overestimation, which can lead to unnecessary expenses, and underestimation, which can result in an inadequate electrical supply. Firstly, consider the general lighting and receptacle loads, as outlined in the National Electrical Code, or NEC, Section 220.12 and 220.14. These sections provide guidelines for calculating the minimum lighting and receptacle loads based on the square footage of the building. However, these calculations often result in higher values than the actual load readings, especially in buildings with dedicated systems for heating, ventilation, and air conditioning, or HVAC, and emergency lighting. Secondly, account for heating, ventilation, and air conditioning, or HVAC, load deductions. In buildings with separate systems for heating, ventilation, and air conditioning, or HVAC, the calculated load can be reduced. To determine the deduction, estimate the heating, ventilation, and air conditioning, or HVAC, load per square foot for the occupied area. A common assumption is 0.5 watts per square foot. For example, In a 10,000 square foot occupied area, the heating, ventilation, and air conditioning, or HVAC, load would be 10,000 square feet times 0.5 watts per square foot, which equals 5,000 watts or 5 kilowatts. Thirdly, factor in emergency lighting load deductions. Similarly, if the building has a separate system for emergency lighting, a deduction can be applied. Estimate the emergency lighting load per square foot for the entire area. A typical value is 0.1 watts per square foot. For a 22,000 square foot building, the emergency lighting load would be 22,000 square feet times 0.1 watts per square foot, which equals 2200 watts or 2.2 kilowatts. Fourthly, consider occupancy deductions. The standard calculation assumes 100% demand for occupied areas. However, the actual demand is often lower, especially in office spaces where not all equipment and lighting are in use simultaneously. A reasonable assumption is to consider a 50% demand factor for occupied areas. For instance, if the calculated load for a 10,000 square foot occupied area is 48,140 volt amps, the reduction would be 48,140 volt amps times 50%, which equals 24,070 volt amps. Fifthly, account for common area load deductions. Common areas such as hallways and elevator spaces typically have lower demand factors. These areas are not fully utilized throughout the day, so a lower demand factor can be applied. A common assumption is a demand factor of 25%. For example, for a 7,000 square foot common area, the calculated load reduction would be 7,000 square feet times 4.5 watts per square foot times 25%, which equals 787.5 volt amps. Sixthly, revise the calculated load. After determining all applicable deductions, revise the calculated load. Start with the original calculated load and subtract the deductions for heating, ventilation, and air conditioning, or HVAC, emergency lighting, occupancy, and common areas. For instance, if the original calculated load is 123 kilovolt amps, the heating, ventilation, and air conditioning, or HVAC, and emergency lighting load deduction is 7.2 kilovolt amps. The occupancy deduction is 24.7 kilovolt amps, and the common area load deduction is 787.5 volt amps. The revised calculated load would be 123 kilovolt amps minus 7.2 kilovolt amps minus 24.7 kilovolt amps minus 787.5 volt amps, which equals 81.12 kilovolt amps. Seventhly, compare the revised calculated load to the actual load. After revising the calculated load, compare it to the actual load readings obtained from current monitoring equipment. If the revised calculated load is still higher than the actual load, consider additional factors that may be contributing to the lower actual load, such as energy-efficient lighting fixtures, occupancy sensors, and variable speed drives on heating, ventilation, and air conditioning, or HVAC, systems. Lastly, document and present findings. When submitting a proposal to local authorities, such as the City Planning Department, provide a clear explanation and supporting documentation for all deductions and calculations. This demonstrates the accuracy of the load assessment and the validity of the proposal to add new electrical installations, such as a 350 amp meter fitting to subdivide existing tenant space. To accurately calculate the electrical load for a high-rise floor, especially when the calculated values significantly exceed actual load readings, several key adjustments and considerations can be implemented. By accounting for specific characteristics of the building systems and usage patterns, a more realistic load assessment can be achieved. This approach is particularly useful when proposing new electrical installations or modifications to existing services. Firstly, separate systems for heating, ventilation, and air conditioning, or HVAC, and emergency lighting allow for specific deductions. Buildings with dedicated heating, ventilation, and air conditioning, or HVAC, systems and emergency lighting can have their calculated loads reduced by considering these separate systems. This is because the standard calculation methods often overestimate the combined load. To calculate the heating, ventilation, and air conditioning, or HVAC, load deduction, Estimate the heating, ventilation, and air conditioning, or HVAC, load based on the occupied area. Assume a load of 0.5 watts per square foot for heating, ventilation, and air conditioning, or HVAC, in the occupied area. For a 10,000 square foot occupied area, this would be 10,000 square feet times 0.5 watts per square foot, which equals 5,000 watts or 5 kilowatts. To determine the emergency lighting load deduction, use a value of 0.1 watts per square foot for the entire area. For a 22,000 square foot building, this would be 22,000 square feet times 0.1 watts per square foot, which equals 2,200 watts or 2.2 kilowatts. The total deduction for heating, ventilation, and air conditioning, or HVAC, and emergency lighting is the sum of these values, which is 5 kilowatts plus 2.2 kilowatts, which equals 7.2 kilowatts or 7.2 kilovolt amps. Secondly, occupancy demand factors can significantly reduce the calculated load. Standard calculations often assume a 100% demand for occupied areas, which is rarely the case in real-world scenarios. Applying a more realistic demand factor can lead to a more accurate load assessment. For office spaces, a demand factor of 50% is often reasonable. If the initial calculated load for 10,000 square foot occupied area is 48,140 volt amps, applying a 50% demand factor reduces the load by 48,140 volt amps times 50%, which equals 24,070 volt amps. This adjustment alone can substantially lower the overall calculated load. Thirdly, common area demand factors should be considered. Common areas such as hallways and elevator spaces typically have lower occupancy rates and usage patterns compared to tenant spaces. Therefore, a lower demand factor can be applied to these areas. A demand factor of 25% is often suitable for common areas. For a 7,000 square foot common area, the load reduction is calculated by multiplying the area by the standard load per square foot, typically 4.5 watts per square foot, and then applying the demand factor. This would be 7,000 square feet times 4.5 watts per square foot times 25%, which equals 787.5 volt amps. This adjustment further refines the overall load calculation. Fourthly, revise the total calculated load by summing all the adjustments. To revise the total calculated load, start with the original calculated load and subtract the various deductions calculated earlier. If the original calculated load is 123 kilovolt amps, the heating, ventilation, and air conditioning, or HVAC, and emergency lighting deduction is 7.2 kilovolt amps, the occupancy deduction is 24.7 kilovolt amps, and the common area deduction is 787.5 volt amps. The revised calculated load is 123 kilovolt amps minus 7.2 kilovolt amps minus 24.7 kilovolt amps minus 787.5 volt amps, which equals approximately 81.12 kilovolt amps. This revised figure provides a more accurate representation of the building's actual electrical demand. Fifthly, compare against actual load monitoring data to validate your calculations. After revising the calculated load, compare it against actual load monitoring data collected over a representative period. This comparison helps validate the accuracy of the adjustments and identifies any remaining discrepancies. If the actual load, based on current monitoring, averages 115 amps alternating current per phase on a 120/208 volt system, the equivalent kilovolt amps is calculated as 115 amps times 3 phases times 120 volts, which equals approximately 41.4 kilowatts or 41.4 kilovolt amps. Comparing this to the revised calculated load of 81.12 kilovolt amps shows a significant difference, indicating that further investigation may be warranted to identify additional factors contributing to the lower actual load. Sixthly, consider additional factors influencing actual load readings. Several additional factors can contribute to lower actual load readings compared to calculated loads. These include the use of energy-efficient lighting fixtures such as light-emitting diode or LED lighting, which consumes significantly less power than traditional lighting systems. Occupancy sensors that automatically turn off lights in unoccupied areas can also reduce energy consumption. Variable speed drives on heating, ventilation, and air conditioning, or HVAC, systems allow the systems to operate at less than full capacity during periods of low demand, further reducing energy consumption. Seventhly, documenting and presenting the revised calculations is very important. When presenting a proposal for new electrical installations or modifications, such as the addition of a 350 amp meter fitting, it is crucial to provide clear and well-documented calculations. This documentation should include all assumptions, deductions, and supporting data used to arrive at the revised load assessment. Clearly explaining the methodology and rationale behind the adjustments helps build confidence in the accuracy of the assessment and increases the likelihood of approval from local authorities. Therefore, the key to accurately calculating electrical loads in high-rise buildings involves a combination of detailed analysis, realistic demand factors, and consideration of specific building systems and usage patterns. By systematically accounting for these factors, a more accurate load assessment can be achieved, leading to cost-effective and efficient electrical installations. By carefully considering these deductions and revisions, a more accurate representation of the building's electrical load can be achieved. This, in turn, supports the argument for the feasibility of adding a 350 amp meter fitting, as the actual load is well within the capacity of the existing 800 amp service. Providing comprehensive documentation and a clear explanation of the calculations is essential when presenting the proposal to local authorities.